So I just want to say a little bit about the use of linear regression for classification. Now, you usually do not, usually people don't use this anymore because it usually is a very restrictive kind of classifier because you are, you will only be able to get good results if the classes that you are trying to separate happen to be linearly separable, right? Given the variables that you have. But nonetheless, they are useful as an illustration of how to approach this kind of classification problem using familiar tools, all right? So I don't want to go through this part yet. I just want to develop the intuition. Okay, so generally you will not find people saying that they use simple linear regression or multiple linear regression to do classification because like I mentioned, it just presupposes that your class labels are linearly separable, and that assumption is too rigid, all right? And you will find that more flexible methods like support vector machine, they will beat linear classifiers most of the time, right? So people don't use that anymore. But anyway, let's look at the theory, the idea. So let's see. Okay, so maybe let's. Okay, in this case, we have the response variable. Like our response variable is the class label. And here in order to use linear regression as a classifier, you have to use this form, which means this is one class, and this is another class, all right? So instead of using most of the time, like for normal modeling work, you will use this as 0, this as 1, okay? But if you want to use linear regression as a classifier, then you use it as -1, yeah, okay? Now, once you do this, you have the following. So let's say we consider one variable data, right? So this will be your class label. And you basically just have 1 here and -1 here, right? Okay. Now, so your data points, right? So basically, so here you will, let's say you take the y minus y bar, right? This is the centered x variable, okay? Basically, you just center by subtraction of the sample mean. So if you have a situation like this, for example, so the ones are distributed like this, and your, right, so then your blue ones, suppose they are distributed like this, okay? Then what happens is that you basically estimate a regression line, all right? So your goal is so you basically have some kind of a mean, right? So basically your regression line will go through this, maybe something like this. Okay, the point is this regression line, this is your y equals to mx plus c, right? So this regression line is estimated using the data here. Okay, and basically this is what we use this this as a decision. So this will be our decision boundary. Okay, and once you have got this, then it's easy to make a decision. So basically, you decide that everything over this side, okay, will be red. All right, and anything that is on the left side, this will be all blue. Okay, of course, then this will be mistakes, right? This will be mistakes. Yeah. Okay. So the idea is very simple. So basically, you put your data on this minus at 1 and minus 1, and then you just treat it as a usual regression problem to get the regression line. So basically, this will be, let's say this is anything that is y. So if your y is greater than this mx, so I think this part is lower, right? So anything below this line. So anything y less than mx plus c will classify as red, all right? And so more than or equal to, you can actually basically set it to equal, classify as blue. All right, for two-class classification problem. Right, so what if you have 3 variables? Let's say you have y equals to mx1 plus mx2 plus another constant, let's say c. So again, this is very is similar. So basically, you have so this is your x1, this is your x2, and on the y-axis, so your third axis here, you basically have 1 and minus 1, right? So basically, it will kind of like stay in a plane, right? So your data points will basically stay in this plane, the plane of 1. So it will sit there, right? So they'll be sitting like somewhere around here, for example. Maybe these guys will sit somewhere around here. Okay. So basically, then you do a regression. So your regression here in this case will be a plane, right? So the plane may be something like cutting through like this. Maybe some plate like this. Okay. So anything above this plane, you classify as blue. For example, anything below it, you classify as red. Okay, so that's the geometry of linear regression classifier. So is it easy enough to understand the intuition?
Yes.
Right, so basically this is what we call a hyperplanar, right? So you can basically have a multi-dimensional, like you can go up to 10 dimensions. Then your hyperplane will be your decision rule will basically be a hyperplane that's 1 dimension less, right? So, but then of course, it's an abstract plane. So you can't draw it. Some interference. Okay. All right. So that's the general idea. Okay. So now let's look at we just try to relate it to the statistics, right? So the thing now is that how do we get this line, right? So basically you have to estimate the slope, right? And the coefficient. So basically in normal regression coefficient, we have beta naught plus beta 1 x. Actually, this is x minus x bar, okay, because it's centered, right? Okay, so you have y equals to this, right? So basically then you want to estimate, right? You want to find so this line is estimated using data, so it's a beta naught hat, right? Beta 1 hat. Okay, so this will apply standard estimation procedures that you have learned in statistics. So maybe I will just go through the theory a little bit. share, new share. Okay. All right, okay. Can you see my screen?
Yes, the linear classifier. Yep.
Okay. So let's, okay. So then you can see that this is your, of course, this is your linear model, right? And I think you're quite familiar with this. So the idea of trying to estimate the beta naught and beta 1 is to use the least squares method, right? So you want to minimize the sum of squared residuals, okay? The least squares approach. So this is your, so for every observation y of I, you will subtract the model, yeah? So this part here is your yi is your observation, and this beta naught plus beta 1 times the x minus x bar, that will be your model value, right? So it's like the deviation between what you observe and the model, and the linear model, okay? And then you square that. So that will be the squared residual, right? So whatever that is not modeled by the straight line is called a residual. So you have a square. Then you add up all of them, okay? So this is a very intuitive way, right? So we are looking at the residuals. Of course, if your fit is good, the residuals should be small, right? So the simple criterion is to find your beta naught and beta 1 is to tune them in such a way that your sum of squared residuals is minimum, right? So then this becomes a minimization problem in mathematics. Okay, so you have an your objective function is now S, and then you want to minimize it. So basically you just here you don't need to apply any minimization algorithm because this is simple enough. You can use differential calculus to do it, right? So you will basically take the derivative with respect to beta, and then set it to 0, right? And then take the derivative with respect to beta 1 and set it to 0, okay? So then you solve, right? So by doing so, you will get these two as solutions. So these two are your solutions when you try to solve the two differential equations. Okay, so I'll leave that to you, okay, how you do that. In fact, if you have studied some statistical theory, you will notice that so this is actually looks like it is actually just based on some kind of some reasonable criterion for finding the alpha and beta values. There's a very nice result which shows that your estimate here, these two estimates are actually your maximum likelihood estimates, okay, for beta naught and beta 1. Of course, if you want to connect it to statistics, then you have to assume that the residuals actually have some kind of distribution, right? Usually is modeled as a normal distribution, right, with 0 mean and a constant variance, okay? But anyway, that is just to let you know it doesn't affect your estimation procedure, right? It's just nice that your least squares method actually is equivalent to the maximum likelihood estimation. So so then you have the estimate for the intercept. So this is the intercept, right? Beta naught is basically just the sample, so the mean of y, right? So basically it's you add up the number of -1 and then you add up the number of 1. So these are the class labels, -1 and 1. Over here they are treated as they are sort of like they're treated as if they can perform a numerical, they make sense numerically, all right? So basically you have then the beta 1 is your slope estimate, and you can see that the numerator part there is basically the covariance, Actually, there's a division by n, but since the denominator also has a division by n, the denominator is the variance of x, the sample variance, right? You divide by n and you divide by n. So your slope coefficient, right, basically is the sample covariance divided by the sample variance of x. Right, so it's actually, if you understand the structure like this, you can recall these things. Otherwise, it will just look like a formula to you without any connection to some statistical quantities. Okay, so your slope estimate is basically the sample covariance divided by the sample variance of x. So you basically can rearrange, and it's just a rearrangement. Now, once you have done the rearrangement, you can express it in terms of the class ratios, right? The number of positive class, the number of negative class, right? So when you sum this, basically you get the sum of xi, right? Because your yi can be positive or negative, right? So these are for the positive cases, right? So when you're positive cases, you basically just sum. So this I basically they index only the xi's where their yi's are positive 1. Okay, they need not follow from 1, 2, 3, 4, 5. It's just saying that this is a set. Huh? Okay, your I is indexing those values where their yi is positive 1, and this one is indexing those sets, those xi's, xj's where they belong to the class negative, right? But since for that yi is negative 1, so that's why when you sum, so you get a part that is negative here. Okay, and furthermore, this one you can simplify, right? So this one is basically just the number of plus classes multiplied by the mean, right, of the plus class. Okay, you can see very clearly that this is the same as the sum of xi, because the mean is the sum divided by n of plus, right? So you have this identity. Okay, so then similarly you can rearrange the sample covariance, right? So if you rearrange the sample covariance, which is this guy here, right? Okay, the numerator. So so this one you fill in the details. Okay, so you rearrange it, you will get something like this, and so your n is your total sample size, right? Which is made up of those belonging to the sample size of those objects in positive class and those in the negative class. Okay. And then using this, there are some identities here, right? So basically there's nothing much. This is basically just going through the algebra. And finally, you'll go through the algebra here, and you can simplify it as the following, right? So it is twice of the product of the positive class and the negative class, and multiply by the difference, the mean, right, of the positive class and the negative class. Okay, so that will give you the sample covariance. So after that, okay, so these are just further simplifications, and this is the final decision boundary. Okay, so this is the decision boundary that you saw just now, yeah, where you use it to differentiate between the plus class and the minus class. As you can see here, so this is your intercept, yeah. The intercept is the y bar, so it's the average of, it's basically taking, so your y bar basically is taking the number of positive classes minus the number of negative classes, okay? So this is very interesting because of the following thing. So let me just write it down. Okay, so okay. So let's see, your decision rule is the following. Y bar plus 2 pi plus pi negative x bar plus minus x bar negative over the sample variance of x, and this is your variable, okay? So basically your y bar, right? Your y bar is basically the sum of yi's, right? Y equals to 1 to n. And this one is basically your sum 1 for I in the plus group, right? And then you plus minus 1 for I in the negative group, okay? So basically this will be just n plus, okay, I'll just put the circle here for, okay, plus, minus n of that. Okay, so basically the difference between the sample size, okay, of the positive class and the negative class, right? Okay, so which means if you have okay, so this is your x minus x bar, right? So this is your 1, this is your minus 1, okay? It lower, right? So if you have a balanced class ratio, this means your n plus is equal to n minus. In that case, your slope, it will pass through 0, yeah? All right, so your regression line will pass through 0, like this, right? If it's unbalanced, like for example, let's say, suppose your n plus is much larger than your n minus, then basically this will be close to, so your y bar maybe, okay, maybe you get something like this. So it will go high above, and maybe perhaps you will get something like this. Okay, so whether it goes down like this or up like that depends on the slope, right? So this is your slope, right? If your slope is negative, it can be going down like this. Okay. What I'm trying to say here is that this value, this intercept here, depends on the difference between the. It depends on your class ratio, right? Whether it's balanced or not. Okay. So if it's more or less balanced, your intercept will go around here. Well, generally, let's see it. Generally, this, okay, it's either at 0, or then after that, I think it will go out of, or maybe it's at 1, and then so on. Okay. It cannot be a decimal actually. It has to be 0 in integers, right? So we'll go by integers. Okay. So anyway, for simplicity, let's just assume that we have equal classes, right? So then we will have something like that. Okay. And then you have your basically your slope, okay? So if you look at the slope carefully, what do you see here? How can the slope be large? This is your slope, right? So your slope will be large if, so this proportion is already fixed, right? Okay, it's, you can't, there's nothing much you can do here. The part that is important is this part and this part, right? If your x bar plus, the difference here is large, and this one, the variance of x is small. Okay, you can see very easily. So how? Okay, so let's look at the first one. The mean of the plus and the minus group is the difference is very big. So one possibility will be something like this. You have a bunch of values here, and then over that side, because their mean difference is very large, right? So the other is basically sitting somewhere around here. Okay, right? If this is the case, then your slope, right? Your slope may be something like this. Instead of that, the slope will be estimated as such. Okay, this will be the slope, right? And of course, if let's say over here your variance, right? Since your variance here is actually relatively small, right? See, your variance here is relatively small, yeah, the spread. So your okay, let me see. The variance here is actually not, this is the overall, so it's actually not that small. Actually, okay, in this case, you get a slope that is large simply because the separation is large, yeah. The other case is when your variance of x is small, and this can happen as follows. When the variance of x is small, that means something like this. So there's not much variation along x. So be probably something like this, right? So your variance of x is not like just now spread out, right? So it's rather small, and because it is so small, right? Of course, some of them can come here. Okay, and so on, and so when you do the regression line, it will have a slope that is high like this, right? So that anything that's going towards this side is classified as blue, and this side is classified as red. Okay. All right. So basically, it is just rearrangement, I think. So the trick here is that you, in order to use a linear regression as a classifier, so you have to relate it to the quantities that are associated with the class labels and the data. So these are the class label information, and these are your data. Okay, so this is the strategy, right? You have got to relate it. If you just stay at the estimation stage, right, you may not be able to see the connection, right? And of course, in this case, the proper choice of using -1 as to label one of the classes and one, right? Because then they will lead to the fact that when you have balance, when you have a balanced class ratio, your y bar will be equal to 0, right? So it produces a nice geometry. Okay, so is it clear for this example?
Yes, I think.
Or anybody has any queries about the technical material? All right. Okay. So I guess okay, this may be sufficiently maybe simple enough. Okay. All right. Okay. So then I'm going to go to the second part on the logistic regression. Yeah. The logistic regression basically is still a linear model, right? Because your model is basically your response is a log, all right? It's the log of the odds. Is modeled linearly, right? With respect to the predictor variables, okay? So in essence, it's still a linear model because it's linear in the predictors.
So are you saying something?
Okay, can you see the notes?
Yes.
Okay, so for logistic regression, so we know that the model, right, is the linearity is in terms of the log of odds, right? So basically you have this, right? Okay. So your beta, so you're probably familiar with these things by now because you're also taking some other courses, and like especially generalized linear models. So they will have some elements related to logistic regression, right? In fact, GLM they may actually look at it more from a matrix algebra perspective. All these things, linear models are naturally connected to linear algebra methods um, because of the fact that you can express this kind of sums, right, as the product of two vectors. And then you can make use of matrix algebra theory to derive results, which is very powerful. Okay. So basically, that's why we express it in terms of the product, right here. And if you rearrange this, meaning that you take exponentiation on both sides, then you will get something like this, right? So this is left. It is quite simple, the algebra. Okay, so so the linear decision boundary is given by the following result. So this is a general result that if you check the previous notes, yeah, the previous notes actually, you can check towards the end there. There's a statement that in general, for any data matrix, right, you can construct a linear classifier with the decision boundary. So a statement is given there. So that is actually a linear model. And then your W, the estimation of W is given by, there's a formula for that, right? So basically, your weight vector, how you get your weight vector is basically a solved problem. Okay, so So in this case, your linear model here, W transpose X is basically equivalent to your beta transpose, okay? So your beta plays the role of the weights here. And your minus T, so basically, and minus T is equal to beta naught, right? Yeah, so basically this is WT times X minus T equals to 0. So your minus T is basically your beta naught. You can actually write it out to see it more clearly. Okay. Now, statistically, to estimate your W, right? All right. So you use something called a conditional likelihood function. Okay. So for example, you observe a certain number of so in this case, your yi is you're using 0 and 1 here. Okay. Your yi are 0 and then 0 and 1, right? So you observe a certain number of zeros and you observe a certain number of ones. Okay. So let's see. Okay, let me see. Let me just check some things. Okay. Okay, so so this is your conditional likelihood. So if you see and yi, okay, if you see particular case, then this will be 1, right? So your yi will be 1. So basically, this one is basically you are kind of like multiplying the likelihoods, the conditional likelihoods together. Okay, this is basically a Bernoulli. Yeah? If you look at this, this is basically a Bernoulli random variable, right? 0 and 1. Okay, so if your yi is 1, then it will take, so the contribution to the likelihood will be this component. If it is actually your yi is 0, then the contribution will be this instead to the component. Okay, so then since they are all independent, so you just multiply them together, right? That's why you have this form, yeah. So then you take the log likelihood, which basically then is you take log on log of a product becomes the sum. So the yi comes down, okay, and here since your yi here will be, so over here this will be the sum of so since this is just 0 or 1, so this will be just basically the number of elements in I that's in the plus group, and this one in the minus group. Okay. So then you want to maximize, right? Your beta, the maximization of your vector beta hat, right? Is basically this is just for formality lah. It's the argument that maximizes the log likelihood function, right? So basically, is we are asking like what should the values of the beta vector be so that your log likelihood is as large as possible. Okay. So it can be shown that beta hat can be found numerically subject to the condition. Okay. So your beta hat actually needs to use a numerical method to do it. Okay. Which actually happens in the when you run R or some programs. So this is what they do. They do some numerical procedure with some constraints. Okay, with this constraint. Okay. So then let's look at the result here. Right, okay. So this is the logistic regression decision boundary. Let me see. This is this is an example of actually this is not y. This is actually this is probably two variables x1 and x2, because your y is basically no, it cannot, this cannot be the response, because otherwise you'll be just restricted to 0, 1. This is actually another, this is on the two-dimensional space, yeah. So your basically your y is actually on the third axis, yeah, which is coming up from the diagram. So actually, I think I confused you. This is not y. This is actually, you can put x1 here, and this is x2. Okay. So let's say, so basically you look at the scatter plot, you'll find that it's actually linearly separable. This line that you get here, right, that you estimate is basically a plane. Okay, it's actually a plane. It's actually the plane that you kind of like, if you look, you have to think of it as a three-dimensional kind of object, where this is staying at y equals to 0, there's one part, and then there's y equals to 1. Let's say the black one, right, is 1. So the black circles is kind of like you have to lift them up, yeah? They are staying in like maybe they are staying in the space of your, how do you put it? So the plus, they are actually staying on the flat surface, whereas the circles, they are kind of like projected upwards, yeah, towards you. Okay, you have to have some imagination like that, right? And then this plane is the regression plane, the hyperplane that is separating these two classes. All right. And then when you project it to 2 dimensions, then you get this line here. Okay. And if you plot it in terms of the probability, right? That means if you plot, where's the probability? So this is a probability, right? So if you have got the estimated beta put in here, you can plot the probability, all right? And then you can actually visualize it. Okay. Right? You can visualize. So this part, I center it so that it's the visualization is better, right? So you plot the probabilities, all right, by against the regression line here. So what you get is you get a sigmoid function, right? Because just now the function that you saw, 1 over 1 plus exponential of minus beta transpose x, that is what we call a sigmoid function, right? So when you plot it, it looks like an S, right? S-shaped function. Okay. So basically, you can see that these are the symbols are the plus and minus. You see that they are kind of like mixed, yeah. Okay. And one way to use, so there are basically 2 ways to use logistic regression for classification. you can either use this decision rule. All right, you can either use this decision rule, which in that case it becomes more like a kind of a geometric method, right? Because you are using you are doing decision, you are making classification decision based on some geometrical object, right? Which is the plane, hyperplane. Or in this case, you can think of it as the following. Now, these probabilities, you can think of them as the probabilities. So if you collapse this, if you collapse them, collapse all the points, yeah, to the probability axis, and then you draw a histogram. So basically, you're going to get a very skewed histogram. So then you can pick some kind of cutoff that will give you some kind of good performance metric. So maybe let me just draw it. Okay, just now you have that situation. So it's more like you have your x1 and x2 here, right? And this is your y. So you have basically 0 and 1 here, right? So basically just now you have some situation like this. Okay, which I will suppose that the plus are labeled 0. Okay, this is 0. And then you have the circles. Those circles, they will stay at 1, the plane here. Right, just now, so they are staying on this plane, right? So minus equals to 1. It doesn't matter you use which one as plus minus, okay? Right, okay? I mean, like if you make a projection, right? If you make a projection onto the plane here, then that's why you can get the two-dimensional plot, right? Now, so the decision plane here will be something like we saw just now, maybe something like this. Okay, so that may be some plane like this. It's actually maybe some estimated plane that's like this. Okay, some plane that's like cutting like this. Okay, so you project. So basically, when you project, you'll see this line. All right. So one is you can. So basically, so this is your hyperplane, right? Okay. So anything that is above or so you can consider like above or below that plane, right? So the same idea as you use in linear classifiers. You can use that to do decision making, or the other way is to do the following. So just now you had so these are the probabilities, right? So these are your beta transpose x minus x bar, okay? So basically 0 to 1, and you got something like the following. Okay, so basically if you project them onto this axis, the probability, right? So you'll find that you make a histogram, they will become like this for the black one. Whereas for the red one, when you project, so because there are more here, right? So they will become something like this. with some overlaps. Okay, so then your how you are going to make a decision. So you basically need to consider like you can consider cutoffs, like let's say you space out, right? You space 0.01, right? You make spacings. So you consider all these cutoffs. And each cutoff, so if you use this cutoff, anything to the left, you classify as black, anything to the right, you classify as red. Then you can compute a classification matrix. So this is the predicted, this is the observed, right? Okay, so from here you can have a classification matrix and you can calculate things like sensitivity, specificity, and accuracy, right? And so on and so forth, right? So each of these cutoff, right? Each of these cutoff will have a contingency table, classification matrix. There are many, okay? And then you pick the one. So pick the cutoff that maximizes some metric, some desired metric. So this can be, so basically it's like argument that max some metric, like for example, it can be accuracy. So max over the cutoff, right? So your cutoff is from 0.01, 0.02 until 0.99, okay? It's basically you find, right? So maybe it's this one, for example. Okay, then basically then you just use this cutoff, right? That means anything that falls above this line, you will classify as black. Anything below it, classify as red. Okay, so this is how you can also use the probability values, right, as a way to perform classification. All right, so yeah, so when you do logistic regression, there are two ways to approach this. They are more or less the same. So so I would say so in this case this is very linear, right? So this depends on a linear. So basically when you use this rule, this is very linear. This one may be slightly more sophisticated, right? Because you're you're basically finding some kind of cutoff that optimizes some metric. Okay, so that's the general idea. All right, for the some theory on how to estimate the beta vector, right? The values of the beta vector, and also how you translate in practice. Okay. All right. Okay. So so it's 7:30 now. I think we will take a break now. Okay.